This tutorial is going to be about solutions. We're going to talk about what solutions are, how to prepare solutions both from a solid solute and diluting a concentrated solution. And then we'll also talk about reactions within solution and how to do calculations there. Those are called titration problems. Okay, so first let's define what a solution is. Solution is a homogeneous mixture. It's a homogeneous mixture, which means that there is no definite proportion or composition. That's an important feature, okay? The components of a solution, it's made up of a solute and a solvent. And the solute is the substance that dissolves, or the component, the substance that dissolves or changes its state when it goes into solution. Whereas solvent doesn't change. And in lecture, we will talk more about these components and give you a little bit more context. For now, this is sufficient for you to understand what we're going to talk about in this video. Since we're dealing with a mixture, right, we have no definite proportion, no definite composition. So in order for us to know what is the solution or what's there, how much is there, we have to express it in concentration. Concentration tells us how much of the components are in the solution, primarily, usually with respect to the solute, how much solute there is per solution. So the concentrations, there are two main types of concentration units. The first one is called molarity. And I'm capitalizing because it's the beginning of the sentence habit, but it is not a proper name, so you need not capitalize it. So we have molarity, and molarity is, by the way, is symbolized by capital M. And when you see capital M, you will call it molar. You'll just say molar, okay? It's defined as the moles of solute that are dissolved per liter of solution. You need to know this definition. This is very important. Okay, so molarity is moles per liter. It's not grams. Molarity is moles per liter. Okay, the other type of concentration is percent. Now, there are different types of percents that we can use, or you might see. One is mass by mass. So mass percent is, percent in general is part per total. So mass percent is grams of solute per grams of solution, again part per total, times 100. Another type of percent, if both the solute and solvent are liquids, then you have volume percent. And this is not as common that we come across this in general chemistry. However, if you do, volume percent is just that, part per total in volume. So it's milliliters of solute per milliliter of solution times 100. Now, a third type of percent that you may come across, if it just says percent and it doesn't specify, oftentimes it's this third type, or it may be called mass volume percent. And it's pretty much like the name indicates. It is going to be, you know what, let me write it over here for more space. It is going to be grams of solute per milliliter of solution times 100. So you should know these definitions of concentration so that you can work problems or do conversions using the concentrations if that's what you need to do. Okay, so now that we have some working definitions and knowledge about concentration and what solute and solvent are, let's work a problem in making a solution. So these first two things that I'm going to give you, first two problems that I give you, the type of problem is dealing with solution preparation. Okay, so the first problem that we have is to determine the concentration, and this is in molarity, of solution prepared by dissolving 75.0 grams of sodium chloride in 250 milliliters of solution. Okay, let me give you a moment. Pause the video and see what's given and what you're looking for, and go as far as you can in working the problem and then come back. Okay, to work the problem, we have to see what we're given and what we're looking for. Because I gave you the problem and I had already prefaced it, this is a solution prep, we already knew that. However, if I hadn't done that and you just see this problem, let's read through and see if there are any kind of hints in the problem that will help us determine the type of problem that we're dealing with. Determine the concentration. Okay, so we know if it's concentration, we know it's solution right off the bat. But it could be a reaction involving solution or solution preparation. So let's read ahead and see what's going on. So we're dealing with a solution because we want to know concentration. The unknown is molarity. Solution that is prepared, that's the key. So we are preparing a solution. Now, how are we preparing it? Is it a solid solute or is it a solution that's going to be diluted? Let's keep reading. Determine the concentration of solution prepped by dissolving, it's a solid, dissolving 75 grams of sodium chloride in 250 milliliters of solution. Okay, so we have the pieces that are given and what we're looking for. We're looking for concentration, molarity. We have 75.0 grams, it's sodium chloride. We have 250 milliliters of solution. Right? So that's three different things. When we are dealing with preparing a solution from a solid solute, we have four things that we have to have. We have the mass, the volume, mass, volume, concentration, and the fourth one is molar mass. Well, we know sodium chloride, we can calculate molar mass. And let's put that piece here. So molar mass of sodium chloride, we have 1 mole of sodium at 23 grams per mole and 1 gram of chlorine at 35.45 grams per mole. And if we round, we end up with 56.5 grams per mole. Excuse me, that's incorrect, 58 grams per mole, because we have 23.0 grams per mole and 35.5 grams per mole. So that's 58.5 grams per mole. Okay. How do we work the problem? Whatever's given, convert to moles. What can we use from the known pieces to convert to moles? Well, we have grams and we have molar mass. So if we take the grams and divide by 58 grams and a half grams per mole, we're going to get to moles of sodium chloride. Okay, so let's see how many moles of sodium chloride we have. We have 75 divided by 58 and a half, and this gives us 1.282 moles of sodium chloride. Okay, what are we looking for? We're looking for molarity. When we see this capital M, it doesn't really help us. We need to see the units for molarity. So let's, every time you see this M, the molar sign, get rid of it and write the actual units of moles per liter, because this is what's going to help you figure out how to work the rest of this problem. Okay, we've used our molar mass, so let's move that away. We have now 1.282 moles sodium chloride. So for molarity, we need to know moles per liter. So we have 1.282 moles sodium chloride. That's our moles of solute. We have to divide by liters of solution. Look what we're given. We're given milliliters. So we will divide by 250 milliliters, and we'll convert that. We'll divide the 250 by 1,000 milliliters per 1 liter. So you can do that as a separate step if you like. So this ends up being 0.250 liters of solution. And now we have moles of solute per liter of solution. We just calculate and we have our concentration. So if we divide now by 0.25, we end up having a concentration of 5.1282, and we'll write molar, or if you like, moles per liter. Before we finalize our answer, we need sig figs. There are 3 digits here. There are 3 digits here, significant figures. We will round to the third number here, and so this will end up being reported as 5.13 molar as the concentration of this solution. Okay, that's great. So we've seen now an example of how to calculate the concentration from a solid solute and how to manipulate the 4 pieces and how they're worked. Now let's do a dilution problem. Again, I've prefaced it so you know what's coming. But after I write the problem on the board, I will go through and show you some of the telltale signs in the problem that will help you determine that it is a dilution problem. Okay, so the next one is how many milliliters of a 5.0 molar HBr solution are needed to make 1.0 liters of 0.100 molar HBr. All right, so let's analyze the pieces. See what's given and what you're looking for. Okay, we're looking for milliliters of 5.0 molar. So these two are linked. We want to know milliliters of this concentration. And we're trying to make 1 liter of 0.100 molar. So these two are linked, right? This is the volume of this concentration. You have a concentration that's 5.0 molar and another concentration that's 1.0 molar. This is less concentrated or more diluted than this one. Therefore, it's a dilution problem. Okay? So for a dilution problem, we know that molarity times volume concentration liters, concentration times liters of the concentrated solution is equal to molarity times the volume liters of the dilute solution. So we plug in, we have concentration of the concentrated solution is 5.0 molar, or moles per liter. The volume of our concentrated solution, that's our unknown, so times unknown liters. Our dilute solution, the concentration is 0.100 molar, or moles per liter. And its volume is 1.0 liter. So the liters here cancel. We have moles of the HBr. And if we solve for our unknown here, we're going to divide both sides by 5.0 moles per liter. And you have your answer. So 0.1 divided by 5 will be the amount of liters. Notice this is going to be in liters. Moles divided by moles cancel. And then now you have 1 over liters, which is liters. So let's calculate what we get. So we will plug in 0.1 times 1 divided by 5. We get, the answer is, I'll write it up here, 0.020 liters. That's the volume of the concentrated solution that we're going to have to get, and we put it in another flask and we dilute with enough water to get up to 1 liter. However, the problem said milliliters. We have it in liters, so we have one more little conversion. And there are 1,000 milliliters in a liter, so it would be 20 point, there are only 2 sig figs, so 20 milliliters would be required. So you would extract 20 milliliters of the 5 molar solution, and you put it in a 1 liter volumetric flask with some water in it, because you're diluting. And you place your 20 milliliters into the water until it's all homogeneous, and then you dilute up to the mark to make 1 liter, and it would be 0.1 molar concentration. So that's how we calculate making a solution from a solid solute and now diluting a solution. All right, so that's the third type of problem that we have discussed. Let's go back to the first type of problem where there is a reaction. And now instead of having grams of of reactant or product, and how many grams of this and how many grams of that do you produce, or moles, what if they're dissolved in solution? So the reaction is occurring in a liquid, in an aqueous medium. So let's say that we have, let me just give you a problem. What is the concentration, again this means molar, of KOH if 35.0 milliliters of KOH solution, the same thing, required (29.6 milliliters of 0.150 molar HBr to neutralize. Okay, so let's take a moment, pause the video, and determine what's given and what you're looking for, and see if you can work the problem. Okay, so the parts that we know, let's see, reading through the problem again. What is the concentration of KOH? So this is our unknown. So we're looking for molarity of KOH. That's what we're working towards. We are given 35 milliliters of the KOH. So this is KOH. And we are also told that we have 29.6 milliliters of 0.10 molar, and it's HBr to neutralize. Okay, so this is a neutralization reaction. This is not solution prep because it's two different substances. So there's a reaction. We need to write and balance the equation and follow the 4 steps and get to what we're looking for. Okay, let me write the equation and then I'll erase up here and do the work. So we have KOH, and it is reacting with HBr. So this is a neutralization reaction. It's also double displacement. So we're going to switch the ion combination we have, then potassium bromide and water. Pieces, we'll put them underneath each one. We have 35.0 milliliters of KOH. We're looking for its molarity. We have 29.6 milliliters of HBr, and its concentration is 0.150 molar. So where do we start? This is the unknown piece. So we're not going to start over here. We're going to start with the other substance, use whatever is given to convert to moles, use the mole-to-mole ratio, and then convert to what we're looking for. Just like we had done in the other stoichiometry problems that we saw in a previous video. Okay, so we have, by the way, let's get rid of this M. Let's write moles per liter. Now we actually see the units that can help us work the problem. Okay, we have milliliters and moles per liter. We're trying to get to moles. So if we take our volume, 29.6 milliliters, in order to convert to moles, the volume has to be in liters. So we're going to divide by 1,000. And now this becomes liters. Okay. And we're going to now multiply by the 0.150 moles HBr per liter, BR, over 1 liter of the HBr solution. The liters cancel of HBr and we have moles. Now we've taken all of this, we've converted to moles. Now we can go from given to what we're looking for through the molar ratio. There is, let's write our units first. We want to get rid of the moles of HBr and get to moles of KOH. Our molar ratios from the equation 1 to 1. Moles of HBr cancel. Okay, so now we've taken what's given, converted it to moles, went from moles given to what we're looking for. Last step is convert to the desired unit. Look at what we're trying to get. Moles of KOH per liter. Look what you're given. You're given the volume, and you just calculated moles of KOH. So let's see how many moles of KOH we have. So we have 0.0296 times 0.15 times 1 is 0.004440. This is moles of KOH. And this is per this much volume, 35 milliliters. But the milliliters have to be in liters because it needs to be moles per liter. So we're going to divide by 1,000. So move the decimal over 3 places. And now we're going to divide the moles per liter. And we get a concentration of our KOH. The molarity of KOH is 0.127 molar. And there's our answer. So it's the same 4 steps, same thing that we had done before, except the pieces are a little different. It feels different, it looks different, but it's the same conceptual 4 steps. And that does it for solutions.